Hello everyone. Today we're going to continue with the rotational motion in chapter 10, but I would like to start with a review as we usually do. So what we've seen so far is we discussed translational motion and then we kind of do a mapping and use the same constant acceleration equations for the rotational motion. So let's just start with the mapping and kind of remind ourselves what were the units, what the letters are, which symbols we use, and what the relation between translational and rotational. So in translational motion or linear motion, we had in one dimension, we had x as our position, right? And this was in meters. Now we have theta, which is in radians. Okay, so these are the SI units. And usually we do convert these, convert the units, that whatever given in the problem to these, unless we can, like there's an example last time we kept the units in revolutions per minute instead because it was easier to do that way, and then they were asking us to find the answer in that. So just be careful with the units though, okay? That part is kind of where we make mistakes. So the velocity, linear velocity, is in meters per second. Angular velocity is omega, and that is radians per second. And the acceleration, linear acceleration, is in meters per second square. And angular acceleration is alpha, and it is in radians per second square. Okay, so for the conversions of theta, we have the conversion factor. It may not be given in radians. So if it is not, if it is in degrees, for example, then you need to use this conversion factor to convert it to radians. Sometimes it's also given in revolution, or it's also known as like one cycle or turns or rotation. That's all mean like one revolution. So you can convert to 2 pi radians that way. And in terms of units, also be careful with omega, because again, it's very common. Unit for omega is RPM, revolution per minute. So you need to use the above conversion factor to convert the revolutions to radians and also minutes to seconds to get the radians per second. Okay, so be careful with the units. That's kind of the starting thing. I usually take care of my units conversions in the beginning, and then so I don't have to worry about it and I don't plug something wrong by mistake. And I always carry out my units to double check that I'm getting the right answer. And also recall that radians is dimensionless. Okay, so you may get radians at the end, but kind of when you're checking the, especially when you're doing a unit analysis, kind of radians is kind of not there, okay, because it has no dimension. So kind of keep that in mind. Don't think that it is changing your dimension. Okay, so and then we did use the constant acceleration equations. So this could be a linear acceleration or a rotational acceleration, right? Or angular acceleration. So we, in the linear case, we had, or translational, linear, and we also have rotational. So let's just write those down. So we have the position, again, if I'm considering one-dimensional case, x0, and then we have v0x t plus 1/2 ax t squared. And also we had the velocity vx equals to v0x plus axt. So the position, we are using the mapping. X goes to theta, v goes to omega, a goes to alpha, right? So x becomes theta here. That this is theta 0 plus omega 0t plus 1/2 alpha t squared. And this becomes omega, and initial is omega 0 plus alpha t. And those are the two equations that we have. Again, we still do step-by-step process. Once we make sure that acceleration is constant, then we can apply these. Okay. So this was the other things that we used last time. And now, especially last class, we did look into something else. We wanted to relate the linear motion to the angular motion or rotational motion, right? The relation between them. That means, so if you look at the above equations in the linear and rotational, they are kind of separated, right? Either you have all linear stuff or the rotational stuff, but they're not mixed up. To relate those, we start from the arc length equation. And we said that arc length is S, the radius R, and the angle that you make when you turn the object was theta, right? So this is arc length is the linear length and theta is the angular length, okay? And we take the derivative of this, we got the velocity, ds over dt is v, linear velocity, and d theta over dt is angular velocity. And r was constant, so we put it out, it didn't affect our, it was a constant in the derivative, right? And then we did take another derivative, and we got acceleration on the left side because dv over dt is acceleration. R was still constant, and d omega over dt is alpha. So, but we learned about two different accelerations, right? We had a translational one and a radial. So which one is this? The way I remember this is thinking about where this equation comes from. It comes from this velocity equation. And this velocity is, so you have an object, let's say, or this is the path of the object maybe, and this is your, this dot is maybe your object. And this is the tangential velocity v, and this is from the radius, from the center, this is your radius, right? And this is your omega. It's out of the page or counterclockwise. So this is the relation right here, okay? What is this velocity? You can see that, right? It is tangential velocity. That means this is going to give you tangential acceleration then. That's really all I need to understand. It's not a memorization. And the tangential acceleration is then related to the radius and the angular acceleration because alpha is d omega over d theta, right? So tangential acceleration depends on omega as well, but it is the derivative of it. Okay, that means if there's a change in omega, then we have tangential acceleration. Another way of saying that, if there's alpha, if it's non-zero alpha, then we have tangential acceleration. And the other acceleration we learned is in chapter 6. We started in chapter 4 when we talked about uniform circular motion. That was the radial acceleration. That we learned it as centripetal acceleration, center seeking, right? And we know the magnitude is v squared over r. That v is the same v as I drew here. It is the tangential velocity. But using this equation again, you can write this in terms of r omega squared. Okay, square that and now divide by r. This is what you get. So you can also see here that I want to highlight this. Tangential acceleration depends on the change in omega. Radial acceleration depends on omega squared. Okay, so if you have omega, non-zero omega, you'll have radial acceleration. But just because you have an angular velocity omega, it doesn't necessarily mean you will also have tangential acceleration because that omega needs to change. If there is a change, then you will have the tangential acceleration. Okay, so the equations really clearly defines what they are. So I want you to really use these equations, understand them very well. And I also mentioned last time in the video when we solved that problem that when they ask you to find the acceleration and they are not specifying whether it's tangential or radial, you cannot assume one of these. You need to assume that it is the total acceleration they're asking for. So what is the total acceleration? Since we know that one of the accelerations are radial, the other one is tangential, right? So they are going to be perpendicular to each other, and these are going to be the kind of the components of the total acceleration. So you can apply Pythagorean theorem for that reason because they are perpendicular to each other, and then square them, add them up, take the square root, and that's going to be your total acceleration. You can even find the angle for a given time, so it will be the instantaneous case, but you can find the direction as well, but this is the magnitude here. Okay. So these are the things that we covered so far. We did solve a problem, and I'm adding an in-class problem today. So again, once after you revise this, you do this review, I would suggest try to do the in-class problem your own first, and then check the next video for the solution or the PDF for the solution. Okay, and after that we will continue with the workbook.